This is the last chapter. Hooray, hooray. And chapter 18, electrochemistry. One thing you'll notice about the printout for the slides is somehow, instead of left to right, top to bottom, I got it top to bottom, left to right. But they are numbered, so it should be easy to follow. All right, let's talk about electrochemistry, which is the study of chemical changes and the electrical energy that's transferred in the process. We need some terms, though. The terms that are used, these two, oxidation, oxidation and reduction. Anytime we're discussing electrochemistry, think in terms of electron transfer. Electrons are moving somewhere, going from one place to another. And when they do that, we define those terms. The oxidation of any substance is one that loses electrons. This refers to a loss of electrons. And reduction is just the opposite. It's a gain of electrons. And these two processes always occur together. You can't have one without the other. So if there's something being oxidized, something else has to be reduced. In a chemical reaction, all things are neutral. So if electrons are transferred in the process, overall process is neutral. We don't build up any electrostatic charges. That's physics. And the substance that's oxidized is the substance that causes the reduction. So anything that's oxidized is a reducing agent. And conversely, anything that's reduced is causing this substance to be oxidized. It's the oxidizing agent. I'm going to keep doing that. Oxidizing agent. Okay, there's an easy way to remember this, oxidation reduction. It's the acronym OIL-RIG. Oxidation is loss. Reduction is gain. All right. So in order to determine the movement of electrons, what's oxidized, what's reduced, we need a way to, actually it's a bookkeeping scheme of electron movement called oxidation states. In fact, I'm going to introduce you to a famous scientist here in a few slides called Michael Faraday. And he was the one who proposed this system of oxidation states. He was working in electricity and electrochemical reactions, and he needed a way of bookkeeping, so this is what he came up with. And it works pretty well in many cases. It doesn't cover all bases, but it's fairly consistent. So first of all, if we have an atom as an element in its most stable form at room temperature and pressure, its oxidation state is 0. So if we have gold, right, solid gold, its oxidation state 0. And we put the oxidation state in this place. Just don't mistake it for charge. It's not always charge. It's a bookkeeping number. And if we have oxygen, which is most stable as the diatomic, then each one of those oxygens is considered 0. Okay, that's the first one, the easiest one. If you have an ion with a charge, like let's say we have sodium, like that, its oxidation state is the charge. Okay, or if we have chloride, its oxidation state is -1. Okay, if we're trying to decide, because all the rules don't cover every element in every compound, we're just nailing down a few of them so that it enables us to calculate the others. Okay, so for oxygen in a covalent compound, we give it an oxidation state of -2. So water, for instance, that would be a -2. And well, for this example, we have rules for both of them. -2, hydrogen is usually +1. So that gives us 2 pluses and a 2 minus, so it's neutral, cancels out. The exception to that is whenever you have a peroxide. Anytime you have a compound with 2 oxygens together, and then they're connected to something else, some other groups. It doesn't matter what they are. They're usually carbon or hydrogen, maybe. For instance, hydrogen peroxide would be like this. And both of these together are -2. So each one would be -1. Okay, that's the exception to this rule. All right. And notice that this bookkeeping scheme works for covalent compounds as well as ionic compounds. And there's your hydrogen, +1, except that when hydrogen is bound to a metal, it'll be in the second position, aluminum hydride, for instance. And in that case, the aluminum is the positive charge, it's +3, and each of the hydrogens is -1. Okay, that's really the only option you can have for hydrogen because it's only got the 1s orbital and it's already got an electron, so it can either lose that electron or gain another one to fill up the orbital. So that's it for hydrogen. Fluorine. Fluorine is always -1. It's halogen, and you'll notice in your periodic table, if you look at, let's see, where do we have it? In a review document, periodic table. What did I do with it? I moved it. There it is. You'll notice in the upper right-hand corner of those squares are lists of positive and negative numbers. Usually the first one in that list is the ionic charge that would be assigned to that element if it were part of an ionic compound. But the rest of them are, and that one too, are oxidation numbers. So they can be bound in covalent compounds, and those are the possibilities, the most common oxidation states that you will find for those elements. And notice that fluorine only has 1. It's just -1. So whatever compound it's in, you can assign it a -1 charge. The sum of the oxidation states for all the elements in a compound must be 0, as long as the compound is neutral. If the compound's not neutral, then we're talking about a polyatomic ion. And that same rule would hold for polyatomic ions. The sum of the oxidation states must add up to the charge on the ion. Alkaline metals are always +1. Alkaline earths are always +2. Aluminum is always +3. When chlorine or nitrogen are present, and none of the above are part of the compound, then we're kind of stuck. We say, all right, now where do we go from here? Because we don't have a an anchor. Rules 1 through 8 gives us an anchor so we can start calculating the others. But if none of those are in there, say we have nitrogen present with or chlorine present, then we generally go to the more electronegative and give it its positional charge or oxidation state based upon where it is in the table. So nitrogen would be a -3, -1, -2, -3. Chlorine would be like fluorine, it'd be a -1. And if chlorine, for instance, is bound with bromine, right, they're both halogens, which one do you pick? Well, you choose the more electronegative one as the anchor. So if chlorine and bromine are together, we say chlorine is -1, and then we calculate bromine. Okay, so here's some examples. Let's see, K2Cr2 recognized as potassium dichromate. Okay, if we do the whole thing like this, right, there are two ways to figure out what the oxidation numbers are. Well, this is an alkaline metal, it's going to be +1, according to the rules. Oxygen in a compound is -2. Right, so now we can calculate chromium. So I do it this way: 2 times +1 is +2. And 7 times -2 is -14. So what does that give us? That's a -12, right? Okay, we got to balance that -12 with the remaining chromiums. That means together, these have to be +12. With 2 of them, that means each one is +6. And then you can go back and check yourself if you want to add up all the charges. It should come out to 0. The other way you can do that is you can say, well, just forget about the chromium. I mean, the potassium. We know that polyatomic ion is that. And then you can go out from that thing. Because we know what this one is given, that one's given. We have to calculate that. Okay. All right. Now we have a polyatomic ion, which is carbonate. Okay. We know that this one's -2 times the 3 is -6. Total for the oxygens. But we need a -2 left over when we balance. So I say, all right, hold out 2 of those minuses for that charge. That means we only have to balance a -4. So that makes this carbon a +4. Okay. I'm following you. Okay, we're good? No? Okay, it's just math. All right. Let's take it simple again. All right, there's the polyatomic ion. So what's oxygen? -2. Right? My rules say it's -2. Okay, there are 3 of them. So that provides us with a total oxidation number for oxygens of -6. -6. Okay. We need to be sure that we have 2 of these minuses left over when we add them together with carbon, because we have to have that 2- charge. Right? What would happen if I made this +6? Then it would be 0. Well, we can't have that because that polyatomic ion is a 2- charge. So that's why I hold out 2 minuses here for that. And that means I only have to balance a -4 with the carbon. Okay. Okay. I went too fast at the end. Okay. Oh, whoops. I gave it away. Manganese dioxide. Oxygen is -2 times 2 is -4. Right? It's neutral, so manganese has to be +4. Phosphorus trichloride. Here's one where we don't have a rule. Right? So the chlorine is more electronegative. We fix it according to its position in the table, which is a halogen. That means we give it a -1. And remember, this is just a bookkeeping scheme. This doesn't mean that chlorine has a -1 charge. We're just doing this to keep track of our electrons so that when we start reacting them with one another, we can follow where the electrons are going. So a -1 for this chlorine gives us a -5 total for the chlorines. And since it's neutral, that means that phosphorus is a +5. Okay. SF4, well, we know what fluorine is. That's one of the rules. So -1 for a fluorine means -4 total. And sulfur would have to be a +4. Yep. Balance the charges. Okay. It gets easier with practice. All right. So, first semester chemistry, we learned how to balance equations with my budget method. Yeah, there's Brent. Okay. I already got it marked. With the budget method. And it works in great many cases. But there are some situations, and this is one of them, where it may work fine, right, with an oxidation reduction reaction, which we abbreviate redox. That's because oxred doesn't sound right. This method allows you to balance oxidation reduction reactions where electrons are transferred. So if you try a budget method, just a simple budget method for a reaction, and it gives you fits, you just can't seem to get it to come out, check to see if it's a redox reaction. If it is, then you may be better off with the half reaction method. So in the half reaction method, we take the reaction, and in this case, you'll notice that there's some ions missing, right? If you add up the charges, they're not going to be balanced. Not necessarily balanced, because we've left out the spectators. Right? We left out, say, the manganate ion may have a potassium. That's how we got it into solution. The potassium salt of manganate got it in solution. But the potassium is not involved at all in the reaction. It's just a spectator, so we left it out. Iron, Fe2+, maybe we put it in solution as the chloride, right? Chlorine isn't involved in this reaction, so we leave it out because it's a spectator. So don't let that fool you. If you see a reaction that doesn't look quite right, first assumption is we probably left the spectators out. Okay, so this is just, this slide just breaks that equation down into two separate equations, one involving the reduction, and one involving the oxidation. So you'll notice that the way it's written, the reduction, let's see, where's my pointer? The reduction puts the electrons on the left-hand side because they're being added to something over here, right? We're reducing it. We're adding electrons. Reduction is gain. Something is gaining electrons. So they go in here and they're part of one of these on this side, probably the manganese on that side. On this side, and this reduction reaction doesn't have anything being oxidized, right? Because it's just half of the reaction. Only when you put them together do you have the oxidation reduction assigned compounds and elements in the equation. So these half reactions do separate the reduction into one step and the oxidation into another step. Notice the oxidation has electrons on the other side. Okay. One other thing you'll notice is that in the reduction step, the number of electrons going in are the same number of electrons coming out in the oxidation step. That's part of the balancing scheme that I'm going to show you in a minute. Right. This just is an illustration of how that equation would be divided out into reduction and oxidation steps. When we actually balance equations with this method, you arrive at the reduction and the oxidation equations there, where you have a balance of elements, right? Like any balanced equation, and the balance of electrons between the two equations. Once you get to that point, add them back together. So we're going to do one of those. We're going to do several of them, actually. Okay, these are just the steps for doing the method, and I just put them in here for your review. It'll be more useful for us to just take an example and balance it. And so those are the steps we're going to follow. And the first approach that we're going to use is the half reaction method in acidic solution, right? Which means that we've got some protons there somewhere, right? And of course, you know that all reactions don't occur in acidic solution. Some are in basic solution. So we'll get to that one after this one. All right, here we have an example. And we know that these components, Cr2O7 and SO3 2-, yield chromium 3+. These are all in aqueous solution, so I'm going to leave that part out because it gets a little too busy. Okay. So we know that dichromate and sulfite ion together will produce chromium 3+ ion and sulfate polyatomic ion. We know that. That's given. Now what we have to do is separate these out into two separate equations, the oxidation step and the reduction step. So how do we do that? That's where we need our rules for oxidation states. We have to determine which ones lost electrons in the process and which ones gained electrons, and then we can put them in their respective positions. So we did this one before, right? Wasn't that +6? Yeah, that was +6. And this one is already given. So we need to do sulfur here, right? -2 for the oxygen. So that gives us a total of -6, 2 times 3, 6. But we got to hold 2 of those out for that 2-. That means this one is +4. Okay. Do the same thing for the sulfate. -2, this is -8. Hold 2 out, -6, this is +6. Okay. All right. So we can tell that chromium went from +6 to a 3+. So how did it get there? Did it gain electrons or lose electrons? It went from very positive to less positive. It gained electrons. It went from a +6. Sometimes I do tie lines like this. Okay. So this is a gain of 3 electrons for each chromium. Okay. Yeah. This one went from +4 to +6, so it had to lose 2 electrons, right? So this one is a loss of 2 electrons per sulfur. Okay, now we have, let me move this down so I'm picking up too much room. The oxidation step and reduction step. Okay, oxidation, oil rig. Oxidation is lost. Who lost? This one lost. So we've got SO3 2- with a +4 here, and it led us to SO4 2- with +6. Okay, so that means the reduction must be this one. Cr2O7 with a +6 for that chromium, and leads us to chromium 3+. Okay, so now we have our oxidation step, our reduction step. The next thing you want to do is balance all the elements except for oxygen and hydrogen. We're going to catch those a different way. So we have one sulfur here, one sulfur there. We're good. We have two chromiums here. We need two chromiums here. Okay. So now the chromiums are balanced. So how do we balance the oxygens? You balance the oxygens with water. So if you've got 3 oxygens here and 4 oxygens there, you need another oxygen on this side, don't you? Right. So 3 plus 1 is 4. 4 oxygens. Now we just added hydrogen. So since this is in an acidic solution, you add the hydrogens as protons on this side. How many do we need? We need 2. Go. For this one, we've got 7 oxygens here. We need 7 oxygens on this side. So that's 7 waters. We just added 14 hydrogens over there. So we need 14 hydrogens on this side. Okay. All right. Now we need to balance the electrons. How many electrons did we say go from here to here? Well, this had to lose 2 electrons. So which side do the electrons go on when you lose them? On the product side. This one lost 2 electrons. There we go. For each sulfur. This one gained 3 electrons for each chromium. But how many chromiums do we have? We've got 2. So 2 times 3 is 6 electrons. 3 electrons for each chromium times 2. 6 electrons. Okay, now what we need to do is reconcile these 2 for their electrons. This one, oops, nobody caught me.
That's where you can that makes more sense now.
Okay. Take a deep breath. Now we can balance. We need 6 electrons up here. So how do you get that? Well, we got to multiply the whole thing by 3. Because now this is balanced for everything we put into it except the electrons. And the only way to increase the number of electrons is to increase the number of everything else. So 3 times everything will give us 6 electrons down here. This will give us 3 here, 3 there, 3 here. 3 times 2 is 6, and 3 times 2 is 6. Right. So we use that one up. Now we have balanced elements, balanced electrons. We can add these 2 together. Okay. So we got, let's put them in the same order here. We got 1 dichromate. We have, let's put the sulfite next. 3 sulfites. 2 rings. Okay, that gets this one, this one. All right, and on this side now we have 3 water. And we have 14 electrons, hydrogen, excuse me, 14 hydrogens, 6 electrons on the reaction side. So we got everything accounted for here. Yeah. Now the product side. So we're going to have 2 chromiums. We're going to have 3 sulfates. We're going to have, let's put them in the same order. Water's next. 7 water. And 6 electrons, right? Yeah. I think that's everybody.
6 hydrogens.
1, 2. Yes, thank you. 6 hydrogens. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, now we cancel terms, right? Well, electrons, definitely, because that's the basis for our balancing. Let's see. Waters, we got 3 waters here and 7 there. These waters go out, and that leaves us with 4 here. 14 hydrogens. We got 6 hydrogens over here. 6 from 14 is 8. Okay. So our balanced equation. Let's see. I got several slides that do it in order. And we should end up, excuse me. There it is. 8 hydrogens, 2 chromes, 3, 4 waters. That's it. So that's the balanced equation by the half reaction method. Okay.
A lot of thinking.
You have to go methodical, step by step, which I didn't do for that one mistake. You saw I was moving too fast. And it didn't take my time. And check my corners.
Really.
Isn't that what they-
Really gotta take this on.
Yeah, yeah. And that was saying combat training. Check your corners. I didn't check my corners. Yep. Hydrogens would have killed me. Okay, so here we have an acidic solution, right? It tells you acidic. Bromine manganate ion yields bromine element and manganese 2+ ion. Okay, let's see, does this work out? Oh no, it just gives us the answer. All right, we'll do this one. Let's see. Okay, so we got bromine. I better write this in here because we got change in phase. And that can make a difference. Liquid and now for these reactions, we're just throwing all this stuff together and letting them do their thing. Right? We got all these electrons moving this way and that. Later on, we're going to figure out how to tap into those electrons, because anytime an electron moves, it has the potential for, no pun intended, the potential for giving us some usable energy. We're going to get to that in a minute. Okay, so this one's going to be a -1, right? This one is a -2 times 8 is minus 2 times 4 is -8. We need to hold 1 out, correct? Hold 1 out. -7, that means this is a +7. This is a 0. This is elemental, and that's a 2+. Okay, so oxidation step. Oxidation is loss. Who loses electrons? Well, bromine lost 1 electron per bromine to go from here to here. Okay. So we got bromine minus, which, okay, yields bromine 2. Okay. And that leaves, for the reduction, that leaves the manganate ion. Which had to gain electrons. It was reduced. It went from +7 to 2+. That's a gain of 5 electrons, right? Because +7 minus 5 is +2. Okay, so we need 2 bromines here, right? We're done. We don't have oxygens to deal with here. Here we have a manganese and a manganese. All right, that's good. So now we can do the oxygens. We need 4 oxygens on this side, which means we need 8 hydrogens on this side. Okay. we went from a -1 to a 0, which is we had to lose an electron, but we lost one for each bromine. There we go. Reduction means we got electrons on this side. How many? Well, we went from +7 to a 2+, so that's 5 electrons for each manganese. Okay. Now, how do we reconcile the electrons? We got 2 prime numbers, right? A 2 and a 5. So how do you do that one? Cross multiply. 5 times this one, and 2 times that one. 5 times this one will give us 10 electrons, and 2 times 5 will give us 10 electrons here. And then whatever else, so that's like 10 there. We got 5 here, and we have 2 here. We have 16 there, 2 there, and 8 here. Okay, so we used up our multiplier. Now we can add them together. Well, let's save ourselves some work. We don't need the electrons because they're balanced. Right? We've got bromines. We've got 10 bromines. And we have 2 manganese. Okay. So let's give ourselves a little bit of room here. We'll come back to the others. On this side, we have 5 bromine liquid and 2 Mn2+. Okay, now let's reconcile the hydrogens and the waters. We got any hydrogens up here? No, no, we have to keep all the hydrogens. 16 hydrogens. And how about the waters? No waters to cancel up here. So we get to keep all these waters. 8 waters. Now, the other thing I didn't mention before is, once you get to this point, can you reduce this any further? Remember, that was one of the rules. Simplest whole number ratios. Right? 10 to 16, 5. Now, 2 and 5 do not jive. So we got to keep them all. So that's why we have 10 bromine, 16 hydrogen, 2 manganese, 5 bromine, 2 manganese, 2 plus, 8 waters. Okay, at least it agrees with the slide. They're either both right or they're both wrong. Mm-hmm.
It's right to me.
Yeah. Okay. I'm gonna have to pick up the pace. Finish this thing. Okay. Now, in situations where you know that the solution is basic, how do we know the solution is basic? Well, you can stick a pH paper in there, or you can stick an electrode probe for your pH meter and determine it's basic. Right? So, in order to balance an equation in a basic solution, I'm sure there's a way to do it straight, just like we were doing here, and then do the hydroxyls and all that stuff. But I found that it leaves me personally open to mistakes. So I like this method. I call it the fake acid method. You balance it as an acidic solution first. Then you neutralize all the protons, all the hydrogens with hydroxyls. And that's what we're going to do next. Okay, so there's a schematic. You look at it if you want. I'll let you read that on your own. I'm trying to clip it along here. All right, so for this one, we know it's in, where's my arrow? There it is. Balance the following in basic solution. We have cyanide,
We have manganate. We have the, I'm not sure what that's called. And NO2.
All right. So remember when we have carbon and nitrogen together, nitrogen is more electronegative than carbon. So nitrogen is going to be -3. -1, -2, -3. This is going to be -3. And we got to hold a negative out. So we only need to balance with -2. So that one's a +2. This one's -2 times 8 is -8, hold one out, -7 is +7. Did that one before. Okay, now what do we do? Well, we know oxygen's -2. All right, so we have to assume that nitrogen is still -3. Okay. So that's a total of -5, hold the negative out, -4, +4. Okay. And then this one is -2 and -4 total. This has to be +4. Okay. So who's oxidized and who's reduced? The carbon goes from a +2 to a +4, which means it has lost electrons. Oxidation is loss. So we know that cyanide, put that up there, yields, whatever this is. And then that means the reduced ones must be this one. So 4 minus, and then NO2. Okay. One carbon, one nitrogen, good. One manganese. Okay, so now we can balance the oxygens. We need an oxygen over here. That means we have 2 hydrogens over here. Okay. We have 4 oxygens here and 2 oxygens there. So we need 2 more oxygens on that side. That means we have 4 hydrogens over here. There we go. Now we can balance electrons. Right? Oxidize. We lost 2 electrons per carbon. Right. Since there's only one of them, that's all we need to do. Manganese gained 3 electrons per manganese, +7 to +4. Okay. So now we can reconcile. We got a 3 and a 2. So cross multiply again. This is going to be ×2. This is going to be ×3. Let's see. Leave myself a little room here. Okay. So that's a 3. This is a 3. Here's a 3. 3 times 2 is 6. And 3 times 2 is 6. You got 2 here. Use that up. 2 times 4 is 8. 2 times 3 is 6, which is good. 2 times 1 and 2 times 2 is 4. Go. So now we know that electrons are going to balance. Let's see, how about waters? We got 3 waters here and we got 4 waters there. Right? So these 3 are going out, and that'll leave us with just 1. Hydrogens. We got 8 hydrogens on this side and 6 on that side. All these hydrogens are going out, and that leaves us with 2 hydrogens on this side. Okay. So that was a part of the shortcut. Rather than go further with the shortcuts, I'm going to bring everything down and then we can finish it off. So we have 3Cn minus. Then we have 2 NO4 minus. And then we have 2 hydrogens. Right. 1, 2, 3, 2, 3. And then on this side, we have 3 CNO minus. And we have 2 NO2. And we have 1 water, correct? Those canceled out. 1, 2, 3. Okay, so now to convert this to basic solution, we neutralize that hydrogen. Right? When you add a proton together with a hydroxyl, you get a water molecule. We get 2 of them. So if we add 2 hydroxyls, right, that makes 2 waters. Okay. So we got to add 2 hydroxyls on this side. That. Okay. Now we've got waters to balance. We've got 2 waters here and 1 there. So that water goes out and leaves us with 1 water. We use those up. So it's this, 1 water, that, and 2 hydroxyls. And everything looks kosher. Now, test question. If the question is, what's the total of all the coefficients? 3 plus 2 is 5 plus 1. Don't forget the ones. That's 6, 9, 10, 11, 12, 13. So the total would be 13. All right. So now we got our feet wet with a half reaction method. It's good for more than just balancing equations. Because if you can separate, up to this point, like I said, these reactions are occurring in the same container. Right? The electrons are moving and we can't catch them. But if we can take those half reactions, put them in separate vessels, and make an electrical and an ionic connection between the two in such a way that we have a complete circuit, then we have potential for moving electrons. And if we can get those electrons to move outside the vessels, we can grab them. That's what the galvanic cell is all about. Capturing that electrical energy. The reaction has to be spontaneous, right? It's got to move on its own to be a galvanic cell, or otherwise known as a battery. A not dead battery. The reactions themselves, the oxidation reaction and the reduction reaction in 2 separate vessels, occur at the electrode. They have to occur at the electrode because that's where the electrons are produced and they move into the electrode and through the external circuit. So the reactions always occur at the electrode. Okay, so here's a schematic, right? So if we were to separate our oxidation and reduction reactions, by convention, the right-hand one is the reduction side. Now, sometimes you'll find it written switched. So take care, because some people, some authors don't follow that convention. And this is the oxidation side. So those half reactions that we wrote, we could put the oxidation one in here and the reduction one right in there. But for electrons to move, we need a circuit. Right? Even the electricity that comes to this building or your house is part of a circuit. Right? So if electricity comes in to your house from the pole, from the line, right, comes in here, right? You got maybe
Let's see, these are maybe 110 volt lines, and you got 3 of them. Right? This is electrons moving in. Right? How do we complete that circuit? Right? Well, this goes back to the power plant. And this goes down into earth ground. And the circuit is in the earth. So you have to have a circuit or the electrons will not move. And that we're going to use that when we build our battery in the lab next week. You can set the whole thing up, right? And all you have to do is make sure that there's no circuit. It's not connected to a circuit. And so you got these electrodes coming out here, and you got this electrode coming out here. If that's broken, and you have in our case, it'll be a salt bridge, right? You got to have mobile ions in order to complete the circuit. If this is broken, then no reactions are going to occur. And we can do that. And then when we get ready to start the reaction, then we connect them. And you can read a voltage. Okay. We're going to use a salt bridge, but there's a certain inefficiency in the salt bridge. Those electrons have to move through. The salt bridge is full of auger. And potassium chloride in that colloid. That's just the augers in there just to keep the potassium chloride from just going blowing out, right? Keeps it stabilized. Sometimes you can have pure electrolyte of some kind in here, and then just plug it with some porous material there. You can do that too, but we're gonna fill it up with auger that's been mixed up with 1 molar potassium chloride as our mobile ions. Okay, so once we connect these, right, with our meter, it'll register a voltage. And ideally, if this is the reduction side, electrons are coming out here, right? And they're being added to something on this side. They're reducing something. Whereas over here, the electrons are moving in. And they're going like that. In that direction. Okay. And we need this other connection to facilitate the movement of charge. Right? If you're subtracting electrons from this side, that means if we don't add cations on this side, no, anions. We need to move anions in here. We need to move something that's not the electrons, but something that's negatively charged in here to replace the loss of those electrons. And over here, we have to move in positively charged something, right, to keep the balance of charge. So in this case, if it's potassium chloride, what moves? Well, the negatives, the chlorides move out here, and the potassiums move out here. Okay. All right. It's more efficient, if you can do it, to use a porous disc between the two. All you need to do is be sure that you don't have a wholesale mixing of the oxidation and reduction reactions. Just a pathway for the movement of ions. And that's the general scheme for a galvanic cell. These are known, this is a galvanic cell. This is a half cell. This is a half cell. Oxidation half cell, reduction half cell. All right. Let's see, we talked about those already. Salt bridge, porous disc. And that shows the electron movement. We call this side the cathode. Cathode is always where reduction occurs. And the anode is always where oxidation occurs. Right, by definition. Just memorize it. All right. There we go. And that fancy E is supposed to stand for electromotive force or electrical potential for the cell. Okay, so you can think of it as either a driving a pull or a push. It doesn't matter. But something is causing these electrons to move, and we need a way to measure it. Well, the standard measurement for that, the force that's moving those electrons, is the volt. Electromotive force. Now, the volt has is a derived unit in the SI system, and it's derived in such a way that the volt equals the amount of work, 1 joule of work, for every coulomb of charge that moves. Now we have to define coulomb too. Coulomb is named after a Frenchman who was working in that field. They just honored him with the name. Now, we just have to live with it. It's kind of like grandfathered in. But we do have a conversion factor for coulombs and moles of electrons that we're going to use later. Let's call it the Faraday, after Michael Faraday. And that will help us bridge the gap between measurements of voltage and the stoichiometry of the reaction. Oh, we got a video. Get the sound turned up.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Okay, notice in that case, there was no water, there was no hydrogen in that reaction. You don't need them. So some reactions are like that. Also, this reaction, the electrodes are participants in the reaction. It's not necessary in every case. Sometimes you have the reactions are entirely in solution, but they occur at the electrode. So in that case, we need some type of conductor in that solution to pick up the electrons or deliver the electrons. You need something very inert, and platinum works really well.
Okay. So how do we measure cell potential? We've got, you know, we can measure the acidity of a solution with a pH meter. Okay. Well, we have voltmeters also. And if you've ever checked the electricity in your house or on a circuit, you know how to use a voltmeter. And the least expensive way to measure it is with a bona fide voltmeter. The voltmeter is constructed with a known resistance in the circuit. And when you put the two electrodes on the source, then there's a push through one electrode out the other one, and the device measures the current through that known resistance. Right. Let's see. I remember it this way. This is I just went blank. I'll think of it in a minute. But if we know what the resistance is, it's a fixed number. It's a constant. Then we have V over I. If we know this one and we measure that one in the voltmeter, then we can solve for volt, and it reads out that value for you. But in order to do that, there's got to be a current. Current has to flow. And when current flows, it meets resistance, which robs it of some of its push. So this one is not as accurate as another method I'm going to show you in just a minute, but it's a lot cheaper to make. So you can measure the maximum cell potential with this only if the current is zero, and you're not going to get that, not in a voltmeter, because if there's no current, there's no way to calculate the voltage. This is Ohm's law, excuse me. Ohm's law. Okay, so if you really depend on accuracy, you use a device called a potentiometer. And in the potentiometer, you have a calibrated reverse voltage. So you have the circuit here that's producing like that, but in the potentiometer, you have a calibrated reverse current, and it's designated I. And you increase the voltage until the current goes to zero. When the current goes to zero, then the reverse voltage is the same as the forward voltage, only opposite signs. So you don't have to have movement of electrons to use this one. And that is the way you measure maximum voltage for the cell or for any circuit, is using a potentiometer. Okay, they periodically have to be recalibrated, of course. So, and the electronics is more expensive. But if you need it, then you get somebody else to pay for it. Like the company you work for or the government. Okay, but digital voltmeters, they're really cheap, right? Inexpensive, and they do a lot more than measure voltage. Usually they're multimeters. Okay, so if you put one in the circuit, then you can measure the voltage. Now, now to the topic of reduction potentials. Maybe, yeah, oh, that's too busy. If I need it, I'll draw it again. You can measure the voltage of any cell that you can build. But suppose we want to calculate a potential for a cell before we even build it. Okay? You can do that if you know about standard reduction potentials. So we have half reactions that are listed, and the standard potential for that half cell is given. Well, what's wrong with this picture?
half cells don't deliver voltage. They only deliver voltage when they're matched with another half cell. Right? So we need a standard half cell to put against our mystery cell and measure that voltage. And every half cell in the list is measured against that standard. And in that case, if it's measured against that standard, like A equals B and B equals C, then A equals C, then you can combine the two half cell potentials to find out what the cell potential for the combination of these two, whatever they happen to be on the chart, put them together, and you can calculate their standard potential. But of course, standard means that we need to know the standards. And if it's got that little zero up there, the standard potential for that half reaction is at 1 molar concentration of any liquids, any solutions. And if the gases are involved, they're at 1 atmosphere pressure. Okay. All right. All the reactions are listed as reductions. So you're going to have something here, plus electrons, however many it takes, and then something else over here. Right, so they're always listed as reductions. So how do you, if you've got a table of reductions, right, one of them's got to be oxidation. So we got to figure out which one has to be flipped in order to make a spontaneous galvanic cell. That's kind of redundant. Galvanic cells are always spontaneous. Right, so what do we compare it to? Well, our standard for comparison is the hydrogen electrode, standard hydrogen electrode. Okay. And the standard hydrogen electrode has an accepted voltage of 0. So any voltage we measure against the standard hydrogen electrode is the voltage of the half cell, the other half cell. Okay. Let's see, we're going to have a picture. I need to draw a picture. Here we go. No. Okay, so if the half cell we're interested in is reported as a reduction, right, then it would be on the cathode side, correct? So we have something over here, and then it goes over here, through our meter, and then it goes over here, and inside that cell is our electrode, and it's going to be flattened because the electrode itself is a gas, right? We need something to conduct the electricity, right? So we've got this platinum inside a tube, and into that tube is hydrogen gas at 1 atmosphere pressure. Okay. And we got a solution over here. We've got a bridge. There. Oops, I didn't go far enough, did it? Okay, so if this one is 0 volts, whatever we measure is this one. Okay. Now, it's not always the case that this electrode will be, this side, this half cell will be reducing. Right? If it's reducing, we're going to get a positive voltage, right? The way it's set up. But if it's not, if the activity forces electrons back the other way, then this becomes the anode. Right? But this is still 0. So any reverse then would be negative voltage. It would be positive in this direction, but negative the way we have set up. Okay. All right. So that's our standard hydrogen electrode. And you've got several slides here. I had to break the table up into several slides because the writing was too small. Oh, I forgot the temperature, 25 degrees Celsius. Okay, so when we do have to reverse a half reaction in order to determine our cathode anode, right? If we have to take a reduction reaction and convert it into an oxidation reaction for the anode side, you just change the sign on the voltage. If you're going to add the half reactions together, right, and make a composite like we've been doing with our balanced equations, then it has no effect on the standard potential. Okay, standard potential is an intensity factor. It's intensive property, right? It doesn't matter how much you have, it's always the same. All right. So there's where we start, and notice that the highest positive value for the half reaction is fluorine gas being reduced to fluoride ion. And then you get smaller and smaller positive values as we go down. This is not exhaustive. This is just was given in your book, and these are very common reactions. And then we just keep going. We eventually get to the point where the voltage drops to 0. And that's where the transition occurs here. So if this was written as a reduction, then this one would have to be the oxidation. This would have to be the anode. These would all be cathodes. We just have to flip this one. And when we flip it, you change the sign of the standard potential, right? How do we change the sign of 0? Doesn't matter. 0 is 0, right? So everything above there against the hydrogen electrode is positive as a cathode. But everything below hydrogen now is negative. So if you add the 0 and the negative together for your half reactions, you get a negative value, and that's not spontaneous. Spontaneous is a positive voltage. So that means that hydrogen has to stay the way it is as a cathode, and everything below it would be reversed, make it positive as an anode. Now, this is all against the hydrogen electrode, right? We haven't compared any of the two reactions together. This is just against hydrogen. But it's a similar concept. When we start to build our cell, we got to decide which one is the anode, which one's the cathode. All right, and there's more. One term they used in that description was called activity. Right? Zinc was considered a more active metal than copper. That means zinc wants to give up electrons more than copper does. So let's go back. Let's find zinc. Zinc ought to be way up here. So zinc. Where is it? Let's see. Strange. There's copper. There's copper. Copper is a positive 0.52 as a reduction. And then zinc must be down here, minus 0.76 as a reduction. But if it's more active, then the zinc has to be oxidized. So we flip the one around, that makes it a positive 0.76 plus that other positive gives us a positive voltage. All right. So most chemistry books, when they say, how do you find the standard potential for a cell? They say you take the cathode standard potential and you subtract the anode standard potential. Right? And that's true. But that just doesn't work well with my way of thinking. Even though it is true, I have a different way of doing it. Just
So the logic is, if once you determine the cathode, then its potential stays the same. Once you determine the anode, since the anode is an oxidation step, you have to reverse it. That's where the negative sign comes in. Let's see. So how about this one? Iron 3 plus and copper metal yields copper 2 plus and iron 2 plus. Let's do that. 3 plus copper metal yields iron 2 plus and copper 2 plus. And I'll write it backwards. Okay, so which one's oxidation, which one's reduction? This one's 0, and the rest of them have their charges. So iron went from 3 plus to 2 plus. It was reduced, right? So our reduction step for the cathode is Fe 3 plus yields Fe 2 plus. And the anode then must be oxidation is copper metal and copper 2 plus. Okay, so we know that this one is going to be reduced. We have to add an electron. This one's going to produce electrons. In fact, 2 electrons per copper. Now, we're not going to bother writing out the complete reaction. We're interested in finding which one's the cathode and which one's the anode. Right, so there are half reactions. This half reaction as a reduction from the chart is 0.77 volts positive. This one, written as a reduction, copper 2 plus plus 2 electrons, would be 0.34 volts. Okay, but we know this one has to be reversed because we just did the work, and that makes this one now minus 0.34 as written. Okay. So to get the standard potential, you add them together, right? So that would be what? Let's see, 3 and 4, 0.43 volts is the standard potential for the cell. Let's see. Well, this slide is going ahead and balancing everything out, which is fine. Balanced cell reaction, there you go. So we would need 1 electron here, so that means 2 here, 2 here, and 2 here. Add them together, and you get that reaction. Okay, but the cell potential, all we have to do is the math, 0.43 volts. Now, once I know that that this is a half reaction and this is a half reaction, and I can look it up in the chart, I can find this reduction is 0.77. This reduction is 0.34. Now, which one has to be made, has to change, has to flip the sign in order to give us a positive value, right? If you flip that one, you get a -77 plus a 0.34, and you get a negative value. So you know that this one can't be flipped. You need to flip that one, right? So that's how I avoid using that formula. I say, which one has to flip to make a positive value? And that's fine with standard potentials. Right? If you want to find the actual potential for a galvanic cell, we need to go to later to the Nernst equation. And for that, you need a balanced equation, and you need to know how many electrons move, how many moles of electrons move. So in that case, you do have to balance the equation. And we'll get to it eventually. Okay, and this says just what I said. The actual cell potential, you need the Nernst equation, you need the stoichiometry of the reaction to determine how many moles of electrons actually move. All right. I'm gonna try to get through this one without confusing you too much. So if we take these 5 species and we want to know which one is strongest to weakest oxidizing agent. So if we want to go, we're going to organize, I'm going to keep doing it. Oxidizing agent. Strongest to weakest. Strongest to weakest. So this is the strong side. This is the weak side. The strongest oxidizing agent is the one that is most easily reduced. So we need to order them by the largest positive standard reduction potential. Large standard reduction potential means ease of reduction. The largest positive value or the largest value relative to the others. All right, so what do we have here? Those would be the possibilities. F2 reduced, sodium reduced, chlorine gas reduced, Fe3 plus reduced. And those are the values that we get. Now, we're actually looking at iron metal, sodium metal, fluoride ion, sodium plus ion, and chloride. Right? So these values don't tell us sodium, fluorine, and iron. So what we would have to do is flip this one, right, to give us the fluoride, because fluoride is part of our list. Right? So what would be the value for that? Well, don't we know? There's more coming. Sodium, we're not sure about that one. We know what sodium ion reduced to that value is. I think it's coming in a minute. There we know the chlorine, and we know the iron. All right. So I get it. I get it. The table only gives us this value. It doesn't tell us this one. But this one should have a reasonably large value. In fact, isn't that? No, because we end up with a negative here. Right? We don't know what that one is. All right, so this is not a really good slide, I have to admit. I'm not sure why. I think we're just going to skip this slide. Here's the explanation. Chlorine is a strong oxidizing agent, stronger than sodium. Right. You can tell that from the use of chlorine gas in bleaching function, making paper or making white cloth. They'll bleach it with pure chlorine gas. That's not a good slide. Let's move on. I think in the interest of time and insanity, we just maybe I need to cut that one out. All right. Instead of drawing the half cells and the salt bridge and all that stuff, which you can do, there's a shorthand method called line notation. And there are conventions that are associated with line notation. the anode is on the left-hand side and the cathode's on the right-hand side. Right, so how do we put them in there? That's the question. Okay. You separate, you put the reactions in such a way that you have this separator, and that's either the salt bridge or the porous disc between the two. Cathodes on this side, anodes on this side. Okay. Then a single vertical line any place means a difference in phase. So if we have a copper electrode, let's see, actually in our example, zinc was over here, right? Zinc solid, and then that's separated from a solution of zinc 2+ ions in aqueous solution, correct? And then the electrons flow from this side over to this side. So on this side, we're going to have the, we're going to have the, we're going to have the copper solid electrode separated from copper in solution. Okay. So it's good practice if you're going to use line notation to always put the phases in. Solid, liquid, gas, or aqueous solution. And if you know it, write the concentrations in. Because if you know the concentrations, then that'll help us in future calculations to do the actual voltage. And that'll become evident in just a minute. Okay, so here's another example. The anode side has magnesium as the electrode. And then it has magnesium 2+ in solution. And for our case, as this one becomes that one, it gives up electrons that move this way. Right? It's oxidized and releases electrons. And then the electrons enter this side at this electrode, and the copper 2+ in solution picks up these electrons and is plated on the copper electrode. In this case, aluminum 3+ picks up 3 electrons and is plated on the aluminum electrode. So you'll notice that if you weigh the electrodes before the reaction starts and then run the reaction for a while, what's going to happen? This one's going to get lighter and this one's going to get heavier because you're adding metal to this one by reduction. Oh, okay. Yeah. Right, there's the anode, there's the cathode. Let's see. What if the solid electrode doesn't participate in the reaction? Right, so are they going to give us an example? Well, you need a chemically inert conductor. That's all that's required. Something that does not enter into the reaction itself, but only provides a conduit for the electrons to move. Graphite rods are cheap, right? Remember the alkaline batteries that you can put in your flashlight? They have a carbon graphite rod right down through the center. Doesn't participate in the reaction, but it provides movement of electrons. Platinum electrodes work too. They're kind of pricey. Okay. So let's see. That one, this one, just in case I need that. How can we describe this galvanic cell if these are the two reactions? Well, notice we're given the reduction potential for silver here as 0.80 volts, and the reduction potential for Fe3+ plus an electron yields Fe2+.
and its potential is 0.77 volts. So which one's a cathode, which one's the anode? They're written as cathodes right now because they're both reductions. If we flip this one to the anode, that makes that one negative, and it's too big, it's negative value. So this one needs to be flipped. Yields. That'd be 3 plus an electron, that's negative 0.77 volts. So we add these two together here, negative and positive, that's only 0.03 volts. Written that way. So this is the anode going this side, and that's the cathode. All right, so let's put the cathode up here first. We've got the silver electrode here, and we've got the silver in solution here. Aqueous solution. Okay. On this side, we have the Fe3 and Fe. Actually, there's no phase difference here. They're both in aqueous solution, right? So you put a comma. But we do need a conductor here. So that's where platinum goes. And then the electrons move from here to here. Right? It goes from this form to that form and loses an electron into this external circuit. Okay. That's the logic behind line notation. Okay. Oh, this is telling us exactly what I told you on the board. So how many electrons would actually move in this reaction? Okay. Just 1 mole, right? 1 mole of electrons to give you that voltage. Let's see. Right. In words, that's what I've been telling you so far. I'll just leave it up there long enough to be recorded. And this is drawn out longhand. But this is the line notation that you would use. We have to assume that there are counter ions in here. Could be chloride. Can't be chloride on this side. So you probably shouldn't use chloride. In case chlorides get across that porous disc, they'll start precipitating your silver. And so probably want to use nitrate. Right? All nitrates are soluble, so nitrate would be a good counter ion for this one. And this is, excuse me, plus. Counter ion for both of them. Just make the nitrates. There it is. I forgot to put aqueous in here. There you go. That would be the line notation for this. Now we're not given concentrate. Well, we are given concentration, so you could put in 1 molar, 1 molar, 1 molar, and the rest are solid. Okay. The cell potential, I'll say this again, cell potential has to be positive as the balanced equation is written in order for the process to be spontaneous, right? And we're going to link this back to chapter 17. We're talking about what constitutes a spontaneous reaction. Now, remember, delta G is negative, the process is spontaneous. But for electrochemical cells, by convention, the voltage is positive, which makes for a potential. So there's got to be a sign change in there somewhere, and it's coming. Okay. Let's see. This slide has us sketching a cell. Potential of the cell, direction of the electron flow, labels on the anode and cathode. Well, this is just an example. If we have copper and silver together, we know that the reduction potential for copper has to be reduced because it's oxidized. I mean, it has to be reversed because it's oxidized. And if we do that, that makes copper at positive 0.34 and negative 0.34, and silver at 0.80 as a reduction potential stays the same, and that gives us almost a half a volt under standard conditions. Okay, let's think about this in terms of Le Chatelier's principle. In this particular cell, where we have copper and silver as the two metals and appropriate solutions in each one, what would happen if we increase the copper ion concentration from 1 molar higher, get higher, right? Think about the half reaction, right? The half reaction on that side is an oxidation, right? Okay, so this is copper going into solution. If we increase the copper concentration in solution, what's going to happen? It's going to drive the equilibrium back toward the copper and consume electrons in the process. So it's going to reduce the potential coming from the anode, and that should reduce the overall voltage available if we increase the copper. Now, it doesn't say, but what if on the other side we increase the silver? Well, the silver is being written like this. So if we increase the silver, it goes the other direction. It would actually increase the voltage. Yeah. Okay. Now we're going to get to, we're going to link these together with chapter 17. Since the cell potential E and the work function value are opposite signs. And why is that? Because remember, our signs are based upon system and surroundings. Right? So anything that adds to the system is positive. Anything that subtracts from the system is negative. So with that being said, the potential then, the voltage, by our definition, is the joules per coulomb. Right? This is the work function, and this is the charge, which is, I know in I think it was chapter 6 in the first semester, we used Q as heat, right? Now it's charge. I think that's why a lot of books use a capital Q for heat and a small q for charge. But then you can get that mixed up with the reaction quotient. Okay, so this is the electrical potential. This is the work function, and this is the charge. But work, if the system is doing work on the surroundings, work is negative, right? And system doing work on the surroundings is giving us work that we can use, right? Because we're out here and this is the system. So if we can use the work, but it's negative, and spontaneous reaction has to be positive, then we've got to introduce a negative sign for the W. And then if we solve for work, the maximum work available is equal to a negative Q times the maximum voltage or the maximum electromotive force potential that's available. Okay. All right. So there's that definition I gave you for a voltage, joules per coulomb. And that's nothing new. Let's see. It's important to recognize that this is a theoretical maximum. You will never get there. The actual work is always less than that calculated. But we got to start someplace. So we start with the maximum and work our way backwards. It's something to shoot for. Okay. W equals minus QE. And here's our conversion factor. Q is in coulombs. Okay, so this is in coulombs, this is in volts, and this is in joules. Okay. That relationship has to remain. But if we're going to use this in stoichiometry, we need to have a relationship between the charge and how many electrons does that represent. And this is the conversion factor. 1 Faraday equals 96,485 coulombs for every mole of electrons. Okay. All right. So we know from chapter 17 that any negative change in free energy, delta G, that represents useful work, right? Gibbs free energy. That's the amount of work that you can get from a chemical reaction. Right? So if we equate the maximum work is equal to delta G, for the galvanic cell, the maximum work, this is also equal to negative Q maximum voltage. Right? And since this already has a negative in front of it, then that's going to mean this positive E is a negative delta G. So that's spontaneous. And then we also know that, let's see, we didn't make that. This is charge per moles of electrons, right? Q is this value, and N is this value. That's my abbreviation for moles of electrons. So 1 Faraday is, this is units of measure. I should say that's units of measure. So Q equals N times F. Okay, and F is this value. So if we know the moles, we know the Faraday, we can calculate the charge, and like any other formula, this is a constant. So these two variables, if you know one, you can find the other. But the Q is equal to NF, and if we substitute that into this equation right here for this Q, it's also equal to a negative of NFE max. Okay. And there's Michael Faraday. He was not a highly educated man. He came from a poor family. So he apprenticed himself for 7 years with a bookbinder. Right? And while he was binding books, he read voraciously on every topic he can think of. And he was drawn toward the sciences. So he found mentors in the sciences, and this one fellow, I think he was a musician, but he had tickets to lectures at the Royal Society. And whenever he got tickets, he gave one to Faraday, and he went and listened to the lectures of these highfalutin scientists. And apparently he was pretty sharp because he was self-educated in that way. Okay. So this maximum cell potential is related to the difference in free energy between the reactants and products. We can relate it that way also. So if you know the reaction, you can calculate the delta G and associate it with the standard potential. So the standard free energy is equal to the negative FE standard. All right. So anytime the E is positive, the cell will run in that direction. And as a consequence, the delta G will be negative. That's a spontaneous reaction. Okay, I'm running way over. If you have to go, you won't hurt my feelings, but I want to finish this. And I'm going to stick around until it's done. Okay. Up to this point, we've had two different half reactions in the cells, the cathode and the anode. Yes. One of the cells we're going to build two types. We're going to build a copper zinc galvanic cell, and then we're going to build a concentration cell using not silver, it's too expensive. We'll use copper. We're going to have a copper half cell in both cells. So if they are at standard conditions, 1 mole in both sides, you get no voltage, right? There's no subtract one from the other, and they're the same magnitude, so you get zero volts under standard conditions. But if we make one of them much higher in concentration than the other one, then we get a voltage, a measurable voltage. It's called a concentration cell. Now the voltage is not really high. In fact, we'll measure it in millivolts. But it is there, it's measurable. In this case, we have, now why did they put the low concentration in the anode and the high concentration in the cathode? That's the question. Well, Le Chatelier says that if silver, let's see, on the left-hand side, anode is oxidation. So we go from silver to silver plus an electrode. That's the anode. And the cathode is silver plus electron yields silver there. Okay. If this one is at 0.1 molar, and then this one is at 1.0 molar, when you put those together, which way is it going to move, right? Let's look at it from this perspective. If we decrease this amount, it's going to draw this direction, correct? Yeah, draw this direction, which on that one would be this direction. So we're decreasing this amount to make that electrode, which drives it this way. So what it's going to do is produce electrons for the low concentration, and gradually, as it does that, this increases in concentration. Right? This is going to go up over time. This one's going to go down over time. Okay. So when does it stop running? When this concentration equals that concentration. Then the cell is dead. Okay. That's how Le Chatelier would explain it. So the low concentration, or if you want to just memorize this, concentration for a concentration cell is always the anode. The high concentration is always the cathode. All right. There's our friend, Walter Hermann Nernst. His work produced a lot of things, but he was interested around this time when he was active. Thermodynamics was really gaining steam, so he was investigating the physical chemistry and thermodynamics of reactions and processes. But he also was looking into other things, which most of the scientists in those days were. But eventually he came up with an equation that we're going to use to determine what is the actual voltage of a galvanic cell if we know the concentrations of all the participants. Oh, I forgot that one. Yeah, he devised the third law of thermodynamics. The one that says a perfect crystal at 0 K has an entropy of 0. Okay. So here's his equation, is that first one. Right there. Right. The actual cell potential is equal to the standard potential minus this calculation. The R, right, gas constant, and that I'm sure that one has joules in it, 8.3145. Temperature in Kelvin, moles of electrons that actually move, and the Faraday constant, times the natural log of Q. And Q is calculated from the stoichiometry of the equation to, like we're comparing Q's and K's. Right? That's the Q. You need to know the Q. Right? But this equation is a little hard to handle, right? Unless you're actually going to be a chemistry major and you have situations that change with temperature is the major ingredient. If you're like us, most of our reactions are going to be conducted at 25 degrees. So we just go in and we substitute 25 degrees in Kelvin for the temperature. And we have a conversion factor for the natural log to the common log. And then when we do that, we come up with this equation. And that's what all that math is all about right in here. Let's see, right here. This just does all those conversions I mentioned. And now we have one that's a little easier to handle. E0 minus 0.0591 divided by the number of moles of electrons times the common log of Q. Right, so if you're going to memorize one, that's probably the best one. And then on the side over here, I just put this general interest, derive the conversion factor for common log to natural log, and vice versa, so that you'd know that I wasn't faking it. Okay, so at 25 degrees, using that modified equation, at equilibrium, Q is equal to K. And the actual voltage is equal to 0, because equilibrium means there's no force to move electrons. Right? So if we take that into consideration and substitute it in our modified Nernst equation, left-hand side is 0, and the right-hand side, Q becomes K. And now we can solve for E0 in terms of K. So if we know the reaction and we measure the potential, the standard potential of that reaction,
we can calculate the K. Or if we know the K, we can calculate the standard potential. Okay, for this oxidation reduction reaction, we have these two half reactions. Right, the what is that on it? S4O6 2 minus. Nothing comes to mind. That's the reduction potential. So that one is the cathode. And the second one, well, the second one is, they're both written as reduction potentials. So which one's going to be the cathode and which one's going to be an anode? If we change the top one, then it makes them both negative. So we need to change the bottom. The bottom is going to be the anode. Right? We're going to flip it into an oxidation state and then add them together. And that gives us 0.67 volts. Standard potential. Okay. So that's what we're doing here. And that's our standard potential for this reaction. And there's the balanced equation. Now, you can't tell from the balanced equation. That's one of the bad things about the balanced equation, because once you put them together, the electrons disappear. So we need to know how many electrons actually move. Well, in this case, before we put them together, we know that 2 moles of electrons moved. Right? So N is equal to 2 for our Nernst equation. Okay, there we go. N equal to 2. So what we've done here is rearrange that equation. Let's go back. Let me see. Oh, there we go. So if we're working from this one, equals 0.0591 over a number of moles times log K, but we want to find out what K is. Right? So we're going to bring everything over here. That's E0 times N divided by 0.0591 equals log K. Okay, so that's where we were at the slide, second slide down, I think. There we go. So there's a log K, there's N E0, and there's your divisor. And log K in this case is equal to 22.6, right? So if that's equal to 22.6, what's K? Well, K, this is 10, base 10. So that means K is equal to 10 to the 22.6. Or 4 times 10 to the 22nd, K. 4 times 10 to the 22nd. That is a huge number. Right, so the reaction is way, way, way far to the right. And that's typical for galvanic cells. Very, very high K values in the spontaneous direction. Okay. The difference between E and E0, when is E equal to 0? At equilibrium. It's a dead battery. Right here. So you can tell the mechanic when they change the battery out, say my battery is at equilibrium. See what he says to that. When is E0 equal to 0? That's for a concentration cell. E0 is equal to 0. Right? Because cathode and anode are the same magnitude value, only opposite signs. Cancel each other out. So here's another example where we have nickel 2 plus and nickel in one side and nickel 2 plus and nickel on the other side, cathode and anode. And notice that I've given subscripts for the cathode as sub C and the anode is sub A, just so we don't get confused. And if we if we want to calculate the actual potential for that cell, a concentration cell, then what we need to know is what is Q. Right? Well, the solids don't enter in, right? But the aqueous solutions do. So the nickel 2+ concentration on the anode side is 1 times 10 to the minus 40. Right? So that's divided by the cathode side, which is in the reactants, right? Divided by 1. And so 1 times 10 to the minus 4th over 1 is the Q. Take the log of that and 2 moles of electrons, and you get 0.118 volts, which is actually pretty good. That's a pretty high value. How many millivolts would that be?
1, 2, 3. 118 millivolts.
When we measure our concentration cell, we're gonna switch it sensitivity from volts to millivolts. Okay. Let's see. We're going to make a galvanic cell at 25 degrees. Nickel electrode is 1 molar. And the silver electrode is 1 molar. Okay. So sketch this one out, show the electron flow and the cell potential. Well, we know that to get the cell potential, we need to flip the top one, make it the anode. Otherwise, we won't get a positive value. So we know that the standard potential is going to be 1.03 volts, about 1 volt. There's the line notation. And since we flip the nickel, it goes on the left with the anode and silver's on the right for the cathode. Okay, and this is the longhand drawing. Okay. There's more. Oh, okay, that's the calculation of the voltage. And then the rest of these talk about batteries. And then we get to a case where we're actually forcing the reaction in reverse, electrolysis. So we're talking about batteries. The only point I want to make with this battery, this is the lead acid battery that everybody finds in their cars. And it's used to crank the engine, run all the accessories. Notice that you have 2 electrodes. One is pure lead, and the other one is lead 4 oxide. Okay. The anode is the lead. This is the anode. So it's going to be oxidized to lead 2+ plus 2 electrons. And this is the cathode. So it's going to be reduced. Plus, no, that's not right. There we go. And this is going to be reduced. Solid. Okay. Now that doesn't take into account the oxygens. But the electrolyte between the 2 plates is sulfuric acid. And because both of these reactions produce lead sulfate, we don't need a membrane between them, right? They have a common electrolyte. Let's see, do I have the equation up there already written? Yeah, there it is. So the overall reaction includes sulfuric acid
Right? And this is the overall reaction where you would add this one together with that one and sulfuric acid and produce sulfate on this side plus water. So that was the only point I wanted to make with this one. You only need a salt bridge or a membrane of some kind between the two solutions if the solutions are different. But in this case, the solutions are the same. And what you get is that lead sulfate is insoluble. It's a solid, and it's deposited on both electrodes. So each electrode, both the lead and the lead oxide, build up a layer of lead sulfate on their surface. And when you recharge the battery, you drive the reaction backwards, right? The alternator in your car with its associated circuitry drives the reaction backwards and forces the reaction to rebuild your lead and lead oxide plates. Well, that's okay as long as the solution can get through to the surface and so that electrons can move the way they need to oxidize or reduce. But at some point, you usually do not completely reconstitute the lead or the lead oxide plates. There's always a little bit of sulfate left. So over time, you build up a layer of lead sulfate on the surface of your plates. And at some point, it's so thick that the electrolyte can't get through to the surface for the reaction to go. And at that point, your plates are said to be sulfated out. That was the old terminology. That's what mechanics understand that. Say, my plates are sulfated out. Oh yeah, I know what that means. That means your battery's dead and you can't recharge it. You have to recycle it. Okay. So that's one of the most common types of galvanic cells in our modern world. Let's see. Yep, that's true. So actually the technology for really high amperage batteries and durability to this sulfating problem is how are the plates constructed so that they can continue to be accessible to the electrolyte. So it's an engineering problem. Okay, this is the inside of a common dry cell that you stick in your flashlights. So the anode is the zinc case around the outside, and the cathode is the carbon rod with the associated manganese oxide and ammonium chloride paste inside. That's why they call it a dry cell, because if you rupture it, it won't just leak out. It's more of a wet paste. Yeah, graphite rod does not participate in the reaction. So everybody knows that the little dimple on the top is the positive electrode, and the little nipple on the top is the positive, and the dimple on the bottom is the negative. So what does that mean? If it's the negative electrode, then the electrons exit from the bottom and they enter through the top. This is another type of battery that's not used anymore because it's got mercury in it. But it was commonly used in things like hearing aids, cameras, so forth. Now they use a different type of technology that doesn't have mercury. This is an interesting one. This is a fuel cell. So you have one electrode on the anode side has hydrogen gas coming in. The cathode side has oxygen gas coming in. And the oxygen is reduced, the hydrogen is oxidized, and you produce water in the middle and a current. This was first used, well, I don't know when it was first used, but I know it was used on the early spacecraft to provide power. Because they had plenty of oxygen. They needed oxygen for the astronauts to breathe, so they had lots of that. And all they needed was to bring along a supply of hydrogen, and they could run their fuel cells. Rather than depending upon solar panels. Because solar panel technology at that time was pretty poor and inefficient. So this was a better choice. The big problem with the engineering here is that originally these fuel cells had to be run at astronomically high temperatures, right? Which made for a dangerous situation if you don't insulate it properly. And that's why they haven't made their way. One of the reasons they haven't made their way into common consumer use. Fuel cells would be a great way to run a car, right? All you need is enough oxygen. Well, you get oxygen from the air, you just need a supply of hydrogen. This is not the only type of fuel cell. You can use methane also. There are fuel cells using methane. But you wouldn't have to sit there and charge your battery, so you could go another couple of 100 miles, right? You just pull up to the station and pump hydrogen into a tank and off you go, just like you were filling it with gas. But there are several engineering challenges that haven't been met yet. One of those is that temperature issue. You have high temperature fuel cell and hydrogen in the same vicinity, right? You set yourself up for disaster, especially when you make a consumer product. You essentially have to make it idiot proof, and they're not there yet. Now, what is corrosion? Remember, on the cathode side, we're taking ions and making them into metal. For example, for copper on this side, making copper. Right? If the reverse happens, if we turn the copper into an anode and turn the copper metal into copper ions, we are corroding it. It's the reverse of the cathodic process. That's corrosion. And we see it typically and mostly in our modern world where iron is involved, like steel, steel bodies of our cars, right? Have you ever been to a used car lot? I mean, not a used car, a parts lot. They usually got big high metal fences around them so people don't have to look at them. It's an eyesore. They have weeds growing everywhere, and they got rusting hulks out there in the field. They're corroding, right? The iron is going back to, it's giving up its electrons, it's being oxidized and turning into iron 3+. So, in short, corrosion is oxidation of a metal. And we've been fighting it forever. This is what on the microscopic scale this is how you would see the surface of anything made of iron would be corroded. And all you need is water and air, right? Oxygen. And you set up yourself a galvanic cell right there on that little water drop. You have an anodic region in the middle, right? The anodic region takes metal and turns it into ions. And then on the other side, those ions combine with oxygen and make rust. That's the cathodic side. And there are your equations at the bottom. So we've devised ways to protect, particularly iron and steels, from rusting, which is another way of saying corrosion of iron. One is by galvanizing. Well, actually, the first one is by painting. Just keep the air and water away from it, right? And so you have to repaint it every now and then. The other way is galvanizing. So if you take a steel bucket, right? And you dip it in molten zinc, you'll get a layer of zinc metal on the surface of the iron. And zinc is a very reactive metal. It will corrode first and spare the iron underneath from corrosion. So they don't, you really have to look hard to find galvanized buckets anymore. They're all plastic now. But it used to be, they're fairly common, right? Grandma and grandpa, right? That's the only kind of bucket they knew was galvanized. And it's got this pretty crystalline lattice structure. It looks like these crossed, if you've ever seen one before.
Older houses have like galvanized piping, don't they?
Yes.
Underground.
Yes.
Yeah, you mess up and put Drano in those, it basically turns to cement. My mom made that mistake one day.
Drano, what's Drano? Sodium hydroxide. Right. You turn the zinc into zinc hydroxide, which is a solid. Yeah. Let's see, where was I? Galvanized. Okay, so you coat it with zinc. It's more reactive. What it'll do is it'll build up a layer of zinc oxide on the surface. Zinc oxide. On the surface, and that will exclude any further corrosion, even of the zinc underneath. So you don't want to polish a zinc bucket because it removes the protective layer. You can also alloy. In other words, you can combine more reactive metals with the steel, or with any metal for that matter. If you can put a more reactive metal into it, then that metal will corrode and sacrifice itself for the iron in our case. So stainless steel is a combination of iron, of course, and it has carbon in it, right? Carbon and iron steel. And it also has chromium. Originally, chromium was 35% by weight. And what it did was, whenever you scratch the surface, right, you put a scratch in it on the surface, chromium is so reactive with the oxygen and air, it instantly seals that wound. So much so that the smallest wound, you can't even tell it's been scratched, but it's still bright shiny. So we make an alloy there. You can also use chromium on the surface like we do with zinc galvanizing buckets. Right? If we electroplate zinc, chromium on a steel bumper, right, you get the vintage cars that you can see at auto shows with the chrome bumpers. They do that with electrolysis, and we're going to look at that in just a minute. But that protects the underneath, the metal, the iron. Another is cathodic protection. So in this case, you separate the active metal from the metal that you want to protect, like this iron pipe. You just make a conductor connected to that. And what happens is usually magnesium. Magnesium is more active, it corrodes more readily. And as it corrodes, it goes from magnesium 2 plus with these electrodes, like 2 electrons. Those electrons go through here. And any corrosion that tries to happen in this pipe is run backwards. Right? It takes any iron that becomes an iron ion is driven back to iron metal. So that's one way to do it. You've also, anybody that's got a water heater is cathodically protected, right? You have a cathode and it dips down into the water, usually made of aluminum, and it sacrifices itself. And it depends on the water. If the water's soft, it's not as needed. If the water's really hard, then it's more effective. When I first moved into my new house, I had a water heater with one of those in it. And after 2 or 3 months, I started seeing in the little filter basket that's in my dishwasher, it's a little metal screen, starting to get these little white flecks in it. And that aluminum electrode was turning into aluminum oxide, having to do with brand new copper pipes. And so I pulled that electrode out, and it should have been about that long, about that big around, and it was down to almost nothing. So I drained out the tank to get all the pieces out, and took that electrode out and put in a new aluminum electrode and filled it back up. No problem after that. It was just at the very beginning, it was protecting the pipes And but once they had developed their own layer of oxide, and it didn't have to work anymore. Okay. So there's your magnesium cathode protecting the buried steel pipe. They used to do this with steel gasoline tanks, buried tanks, filling stations. They have these anodes, and they occasionally have to dig them up and replace them. But when they went to plastic and fiberglass, and that, no problem after that. Same with septic tanks. Now they're made out of plastic or fiberglass. Okay. A lot of these metals protect themselves with an oxide coating. We know that aluminum is extremely reactive metal, but it's so reactive that if you throw an aluminum can out the window, 100 years later, it'll still be there, even after all the paint's worn off, right? The Coke symbols and the Pepsi symbols and whatever. The aluminum will corrode so fast on its surface that it will protect the aluminum underneath. All right. We already talked about that. Oh, which part is the cathode? Well, the cathode is the one that's being reduced. So the pipe is the cathode, and the magnesium is the anode. So it's kind of a misnomer, cathodic protection. You're protecting the cathode with an anode. You'll see this also around ocean-going vessels, ships. Sometimes they'll have chunks of zinc scattered around the hull, or sometimes they'll have a band of zinc around the hull, and they're connected to a direct current source from inside the ship, and it trickles electric charge in there, and it keeps the zinc and the hull from corroding. So when they're sitting at port, if the engine has to be powered down, if the batteries are dead, they can't do it, then the zinc does its work for the hull until they can get the power back up. Okay, electrolysis. Electrolysis is just the opposite of the battery, the galvanic cell. It drives a spontaneous reaction in reverse. And all you need to do that is if you have a reaction, right, that has a spontaneous voltage this way, and it has a voltage for that direction, all you need is to put a source in here that will drive the voltage. Let's see, electrolysis source, greater voltage than the other, and it'll drive the reaction backwards. Now, the terminology still works, right? Now, if you do that, this becomes the anode because it's being oxidized, and this becomes the cathode because it's reduced. So electrolysis, the terminology reverses. All right. You can do that and produce hydrogen and oxygen from water. You can drive a direct current through water. You know that if you react hydrogen and oxygen together, it's a very violent reaction. And it will produce water. That's the reaction that many rockets use to get into space. And the space shuttle main engines operated on hydrogen and oxygen. It's a very energetic reaction, very efficient. What in engineering terms, it's called high impulse. You get lots of force for the amount of substance that's being used. So the reverse reaction would be to take water and drive an electric current through it and split the hydrogen and oxygen apart. In fact, if you overcharge a lead acid battery, you will get that reaction. Right? Once it's completely charged, And if you keep pumping it with direct current in the wrong direction, it can't take the sulfate and convert it back into oxide and lead, right? Because they're already full. I mean, there's no more. So it goes for the water, right? And it turns the water into hydrogen gas. So that's why in the older batteries, they used to be, they have vented caps on them to let the hydrogen out. But now, and for lead acid batteries for the longest time couldn't be used indoors because of that hazard. Now they've got sealed lead acid batteries that have a chemistry built into them that will sequester that hydrogen. So they can put them in things like uninterruptible power supplies for your computers and other things like that. They're sealed. Okay. The stoichiometry of electrolysis is really not that difficult. You've got an amount of current, right, that's flowing through the wire in the reverse direction from the spontaneous direction. And you do it for a certain amount of time. And that gives you a quantity of charge in coulombs. And then we use Faraday's constant to convert that into the number of electrons, and that goes into the stoichiometry of the reaction in reverse. Okay, I should define though, when we talk about current in chemistry or in physics in that matter, it's the I is the term that's used, and the value is amps. Right. So current is 1 amp is equal to 1 coulomb of charge passing a given point in a conductor for every second. Okay, coulomb per second is an amp. So if you know that it's running for a minute, that's 60 seconds at say 1 amp, right, per second. So that'd be 60 coulombs. And then we can convert the coulombs to moles using Faraday's constant. All right, let's see. And there it is again, right? If we know that 1 mole of electrons is equal to, remember from the very beginning when I talked about conversion factors, all you need is an equivalence. If you have something equivalent to something else, you have a conversion factor. So 1 mole of electrons equals 96,485 coulombs. And that gives us our conversion factor. Okay, so let's do an example. An unknown metal is electrolyzed. In other words, we are taking the ion of the metal and converting it into metal solid. Okay. The solution contains this MnO3, 3 of them, right? So what's the charge on that metal? If it's in aqueous solution, the charge on that metal is 3+, right? Because each one of these is a minus. So we know the charge on the metal. All right. We also know that if we're going to have pure metal solid, this needs to pick up 3 electrons for every one of those. So 3 moles of electrons for every mole of metal will give us this. We know that. All right. So now we go for 52.8 seconds is the time for running a charge at 2 amps. So this is 200 amps, which is equal to 2 coulombs per second. And 0.0719 grams. The mass of the metal plated is 0.0719 grams. Okay, we want to know what the metal is. Okay. So how do we tell the metal? Remember, we've done this over and over again. We don't have access to the atomic number, so we have to go to the atomic weight or the atomic mass. So we look for that value, which is grams per mole. All right, we know the grams right here. We need to find out how many moles of metal were plated out. Okay, so if we start with the time, 52.8 seconds, then we can start conversion factors. Right? How many coulombs does that represent? Well, it's 2 coulombs per second. Right? Cancel the seconds. But that doesn't get us to the stoichiometry. So how many moles of electrons were actually transferred? Right? So we need moles of electrons. Right? That's where we need our conversion factor. 96,485 coulombs per mole. Okay. So now we got the coulombs going. That's moles of electrons. Okay. Okay, how many moles of electrons per mole of metal? Okay. So for every 1 mole of metal, we use 3 moles of electrons. So the moles of electrons cancel. Now we got moles of metal. So we can determine how many moles of metal that represents for these grams per mole. That will give us the moles of metal. So let's see, 52.8 times 2 divided by 96,485 divided by 3. And that's 3.64, actually rounded off. 5 times 10 to the minus 4 moles of metal. So the molar mass, or molecular weight, I call it, is grams per mole, 0.0719 divided by 3.65 times 10 to the minus 4 moles. Let's see, 0.0719. 197 grams per mole. So let's find out 197 grams per mole. 2, 20, 90, 90, 90. Pretty close. 196.97. That's gold. Okay. Let's see. Oh, there it is. Okay, so I did it in this calculation. I started off with this one and used that, but I think this makes more sense. Take seconds to convert it to coulombs, convert that to moles of electrons, convert that to moles of metal. It gets better. Okay. Oh, okay. If we're going to plate these out from a solution, say we have a 1 molar solution of each metal, lead 2 plus, copper 2 plus, tin 2 plus, nickel 2 plus, and zinc 2 plus. What's the order in which these will plate out as we increase the voltage? And it does work. You can plate out all of one metal, and you can pull your electrode out and put a fresh electrode and get the next metal, and next and next and next. So the first question we have to answer is, do the metals form on the cathode or the anode? If they're going to be reduced, they form on the cathode. So we're driving electrons into the cathode and plating the metals out. Right? That's the site of reduction. So the reduction potentials will predict the order of plating. Right? The more easily the metal is reduced, that's the first one that'll come out. So the more positive the value, the standard reduction potential will plate that metal out first. Right?
So all we need is to compare the values for each one. Oh, and I've listed them there in order, right? The most positive one is copper. Copper's coming out first, then lead, then tin, then nickel, then zinc. Zinc will be last. Zinc is the more active metal. It wants to be this way more than the others do. It's the most active of this group. So it takes a lot more push. You have to increase the voltage much higher to get it out. So we just go one at a time. Okay. Now, let's see. I should be getting close to the. Yeah, we're just going to talk for a minute about production of aluminum. Back in Louis XIV's day, I ever studied European history. Louis XIV, he was known as the Sun King. Right, everything was bright metal everywhere in the Versailles Palace. And if you want to impress your guests, you serve them with the most expensive finery that you can do. The food is the best, most expensive. The plates and cups and everything were the most expensive. Even the dinnerware was the most expensive. Right? And for the longest time, gold was the best. Right? You just served everybody with gold. Right? And then maybe the secondary diplomats would sit at another table and use silver. But about this time, chemists were discovering how to chemically reduce aluminum into the metal. And it was so inefficient and so expensive to do. If you could get aluminum utensils, they were more expensive than gold. So why not, right? King just said, all right, we're going to serve everybody with aluminum. We don't think in those terms today because aluminum is so cheap. Well, the thing that made it cheap was from the work of, let's see. Oh, I'm getting ahead of myself. From the work of, what was his first name? Hall. I forget his first name. Hall and a Frenchman, Héroult. They came up with this process almost simultaneously across the oceans. Hall was a young chemistry student, and his professor said, if anybody can figure out how to make aluminum metal from its ore cheaply, they will become filthy rich. So he set about figuring it out, and he came up with electrolysis. He figured out how to get the ore into a liquid state. Because if it's not liquid, then the ions won't move. So we got it into a liquid state, and that was a big problem because aluminum oxide ore melts at a very high temperature. So he figured out how to add other compounds to it to bring the melting point down, get it into solution. So that makes aluminum real cheap, right? All you need is free power, cheap power. That's why aluminum plants sprung up in either Pennsylvania, where lots of coal, right? You make cheap power with coal, or in Tennessee, where the federal government paid for electrifying the Tennessee River, right? You get cheap hydroelectric power. Anywhere there's hydroelectric power, then you can put in an aluminum plant. You just have to ship in the ore from the tropics, because we don't have lots of good deposits in the temperate zone. You need the tropics to leach everything out and leave aluminum oxide behind. Anyway, that production of aluminum by an electrolytic process made it cheap, so cheap that we can wrap our food in it and throw it away. We can purify metals like we've just shown, right? You can electrolyze metals out of a solution onto a surface and flake them out. Chrome bumpers, for instance, or you can take cheap jewelry and coat it in a very atom thin layer of gold, and it'll be good and shiny and pretty for a while until, of course, you rub off the outer layer. Then your finger starts turning green.
We can do all kinds of metal plating, purification of metals. You know that the copper in the wires in the houses and transmission wires, actually high voltage transmission wires are more aluminum. It's cheaper and stronger. But in our houses, we use copper wire, and it has to be 99.99% pure. Right? You can't get that easily with chemical means. You can get it to maybe 95%. Well, you put it in solution and drop a pure copper plate in it and run the electricity backwards and plate it out on that plate, and it comes out very, very high purity. Sodium chloride. We can electrolyze sodium chloride. Just melt it and then stick a carbon electrode in it and then run a charge through the vat outside. And you can, actually you need two electrodes. At one electrode, you form the sodium metal, and at the other electrode, you form the chlorine gas. And you take the sodium metal and dissolve it in water and make sodium hydroxide and clean drains with it. Or you take the sodium hydroxide that you make and recombine it with chlorine gas and make bleach. So this is what the Hall-Héroult process. Oh, there's our data, right? Aluminum oxide melts at 2,000 degrees Celsius. But if you add almost 90% cryolite, which is sodium aluminum fluoride, to it, it lowers the melting point, cuts it in half, right? So it takes a lot of energy to melt it, but once you get it melted, then you're good to go. You need a lot of energy to do that. You can electroplate your silverware again. Actually, have you ever tried this? If you do have silverware, right? Bona fide silverware, not flatware, and it gets a corrosion layer on it, right? We used to have to put a paste on the cloth and polish it. Well, if you take that silverware and you take a baking dish and line the bottom of aluminum foil, and then fill it with water, and then put table salt in it, right? And wait for it to dissolve. Then you lay your silverware on that aluminum. The aluminum is a more reactive metal, and what it will do is convert the corrosion products from silver into silver metal, and you can watch it happen. Just put them in there, and it becomes bright, shiny all of a sudden. It's an electrochemical reaction. Okay, here's our sodium chloride electrolysis. Right? At the anode, we're producing chlorine gas. So the anode means oxidation. Right? We're taking chloride, stripping an electron off of it, right? Going from -1 to 0 to make the chlorine gas. And we're taking those electrons, and they go into sodium Na plus. You add those electrons, it makes it sodium metal, and it goes out the other way. That's it.